Okay, you wouldn't know it, but this is my third stab at trying to record this lesson. All right, so third time's charm. Let's try to make this clear. So we are doing related rate problems. This is example number 2. I got a ladder leaning against a wall. So the idea is, imagine this is the ladder and this is the wall here. As if the ladder starts sliding down the wall, that's the scenario. And look at some things that happen. This is moving down the wall at a certain speed. At the same time, this is moving away from the wall at a certain speed, the base of the ladder. This area right here is changing, right, as it falls. And also, if I think about the angle between the ground, let's say this is the ground here. So the angle between the ground and the ladder, that is also changing over time. So there are a lot of things going on, and we're going to try to set this up so we can answer all these questions, and we'll knock them out one step at a time. All right, the first thing to do is to understand the situation, so hopefully you get the idea of a ladder sliding down the wall. And then the next thing you want to do is draw a picture. So this is a pretty simple one. There's the wall and there's the floor. It is important to understand that that's a right angle because a lot of math comes into play if that's a right angle. And then we have a ladder resting on the ground and against the wall. The next thing you do is you kind of think of what it's saying and try to put in variables and constants that make sense. So in this case, that is a 10-foot ladder, and that is always 10 foot no matter where it is when it's falling. It's 10 foot now, 10 foot now, 10 foot now. So I'm going to put 10 for that because that's always 10 feet. This tip of the ladder is a certain height off the floor, and that is not constant. If it's falling, that height is changing, and I'm going to call that h for height, and I'm going to use a variable. Also, the base is moving away from the wall, and that is changing, so I'm going to call that b for base. I know later on I'm talking about an angle between the ground and the ladder, so I'm going to put a theta right there. And I'm not going to put this in my picture, but I know I have to deal with area. Let's call that A, and I know that that would be this region right here. All right, so we're going to knock these out one at a time. We've got a little more work to do. I read it, I understand it, I draw a picture with variables and constants. Now I want to extract the information that is given to me. So 10-foot ladder, that's taken care of. This, do you see those units, feet per second? That's a rate. And every time you see a rate, that's a derivative. So this is going to be d something. That means something is changing. What is changing? As it slides down the wall, that would be this height. The height is changing over time. And by the way, look at these units. These are height units, feet, over time units, t. And that is given as 1.25 feet. Now in this context, you have to add or put in that is negative, because if it's positive 1.25 feet, that means the ladder is going up the wall. If it's minus 1.25 feet, the ladder is going down the wall. This is going down that fast. Okay, that's all the givens. What's the questions? Well, for part A, let's see, I better put it here. These are my givens. Answers will be how fast, that's a derivative, is the base moving? So that would be how fast the base is moving over time. And it says specifically when the ladder is 3 feet from the wall. That would be when this base, I'm going to use a different color here. See, the idea is these rates are not constant. So I want to know when the ladder is 3 feet from the wall. When this is 3, it's not always 3, it's changing, but when it's 3, what would that rate be? Question B is asking how fast something else is changing, and that would be how fast the area is changing over time when the base is 3 feet from the wall. And C is asking how fast the angle is changing. So that would be, d theta over dt, and that's at the same instant in time when the base is 3 feet from the wall. So that's the questions. This is the givens, these are the questions. That's the setup, step 1 and 2. Step 3, Step 3 is what equations make sense here. Now, the killer will be if you try to answer all the questions at once. You do not want to do that. So let's just lock in a number 1. I'm talking about the height, the base, right? See those? Those are the two sides of a triangle. I'm thinking Pythagorean theorem here. So for A, I'm thinking h squared plus b squared is 10 squared. All right, that's step 3. I got an equation that matches my picture. Now, step 4, see all these derivatives? See the dh, dt? I have to take the derivative to get those derivatives. And remember, this is done implicitly because there's no t in the equation. So the derivative would be 2h dh dt plus 2b db dt equals 0, because the derivative of a constant is always 0. Okay, here's 2. I don't know h yet. I do know dh dt. I do know at this moment in time the base was 3. And I don't know dB dt, and I'm not going to bother trying to figure it out because that is the question. If I only knew the height at this moment in time, I could plug it in and get my answer. So look at it. Pythagorean theorem. When b is 3, h would be h squared would be 10 squared minus 3 squared. So h squared would be h would be 91. So h is going to be 9.54 at that moment in time. So that would go right here. All right, I wish we were doing this face-to-face because this is a lot easier to track in the progress and ask me to slow down and repeat stuff if you're live. So let's see. I get this plus 6 dB dt equals 0. See, this is looking nice. This is very doable. So I get dB dt equals 3.98. The units, feet, right? It's moving away from the wall. I think that'd be feet per second. And it is getting further. The distance is increasing, so that makes sense that it's positive. So we just got our answer to part A. 3.98 feet per second. All right, I'm pausing so you can pause it if you want. Now we're going to jump to question B. So all this has to go. Now remember, you can easily get like this feeling that I have no idea what I'm doing, so you got to keep it simple and try to build from there. How fast is the area changing? Area of what? Look at the picture. That's why you need the picture. We're talking about a right triangle, area of triangle. So I pause to let you think of that. 1/2 base times height. Watch what happens when we take the derivative. Now remember, this is implicit with respect to t. dA dt. Be careful here. I'm going to pull that half out. Product rule. So the product rule, if I ignore the half, is the derivative of the first times the second plus the first times the derivative of the second. Now that's a lot of stuff, but I know a lot of this stuff. dA dt is what I want. dB dt I found in part A. I need another marker. 3.98. H I also found in part A. It's 9.54 at this point in time. Plus B is given as 3. Having that picture is very handy. Times dH dt, that was given. So that looked like a big old mess, but look at it. These are all knowns. All I got to do is punch in the numbers, and I got my answer. See, the thinking through it is the hard part. The math in this one was very easy. 3.98 minus 3 times 1.25. I'm going to divide that by 2. And I'm getting 17.11. This is area, right? So that would be square feet per second. Area units over time units. So the area at this point in time, as it slides, is actually getting bigger at that rate. So that will go here. We're almost done. Best for last, trig. All right, C. Look at the picture. This is why you want the picture. If I want to know theta and I know all these sides, we're going to need a trig function. I'm going to use these nice integers. So this would be adjacent over hypotenuse. So just write what you see in the picture. The cosine of theta would be adjacent, adjacent over hypotenuse. I don't want to put those numbers because remember, theta is changing, the base is changing. I don't plug in numbers for these things until after I do the derivative. So first I got to get an equation. I would multiply both sides by 10 here, so I just would because it's convenient. Now I'm going to do the derivative. So this is going to be negative 10 sine theta, and a lot of people trip up here. D theta dt, because that's implicit, equals dB dt. All right. I know dB dt, found it in part A. I don't know d theta dt. That's what I'm looking for. And this is minus 10 times sine of theta. And I would get it by looking at your picture. At this point in time, the sine of theta would be opposite over hypotenuse. So this is going to 3.98 over 9.54 negative. So here's my answer. Now I know trig has been a while, but I'll remind you, one of the main reasons, well, an important thing to know about radians is they are unitless. So this is going to be radians per second. Degrees aren't going to magically pop up in the math here. Feet kind of were embedded in the problem from the beginning, right? But I don't see any degrees anywhere. So if you have unitless stuff and you're trying to find angles, this is why radians are going to be used. So this is getting smaller, the angle is decreasing, and that makes sense. That makes sense. At about a little under half of a radian every second. All right, so I'm going to give you a few problems that are very close. I'm just going to change how big the ladder is and how fast it's falling in this number. And I want you to go through and practice that, I don't know, probably 2 or 3 times. Okay? So try, you got to try. And I will see you next time.